Hello everyone, my name is Sun He. Today I'm gonna present performance testing for cloud computing with dependent data bootstrapping. This is a collaborative research from the University of Texas at San Antonio and the University of Georgia. Nowadays, cloud computing is becoming increasingly popular due to its resource availability, resource elasticity, and cost efficiency. But before simply put applications on the cloud, users have to test their application's performance to see whether their performance goal can be met. The most reliable way to know the performance of their cloud application is by performance testing. However, due to random performance fluctuation, it's very difficult to get accurate testing results. Now let's look at the graph. On the graph are the performance distributions of two tests. Test 1 and Test 2. Both of Test 1 and Test 2 are Yahoo Cloud Serving benchmark on Chameleon Cloud. We first run this application on Chameleon Cloud for 15 hours continuously to obtain Test 1, and then we run the same application for another 15 hours on the same VM machine to obtain Test 2. We can see from the graph that Test 1 and Test 2 are drastically different. We don't know which of them is accurate, or worst case, neither of them is accurate, and this brings about the problem: how to determine the stopping criteria for cloud performance testing to ensure accurate results are obtained. In order to solve the problem for accurate testing results, state-of-the-art testing methodologies adopted different statistical tools. Here is the general steps for the methodologies. First, they have application to be tested, and then in step 1, they conducting multiple performance tests and collecting performance data. In step 2, they estimate the error of the performance test results using statistical tool. And in step 3, they check the estimated error with the user predefined threshold. If it's less than the threshold, they can stop testing. If it's not, they have to go back to step 1 for more test runs. One popular statistical tool for performance testing is bootstrapping. The state-of-the-art methodologies adopted basic bootstrapping to estimate the error in step 2. They choose basic bootstrapping because of the common advantages of bootstrapping, that it's a non-parametric statistical tool. It does not assume any specific distribution of the performance data. However, according to our study, we find that the overlooked internal dependency within the performance test data leads to inaccurate performance results. To be more specific, basic bootstrapping cannot preserve the internal data dependency during resampling, and this leads to inaccurate performance results. Basic BT is one of the state-of-the-art testing methodology that adopt basic bootstrapping for performance testing, and here is an example for basic BT. First, we have the initial sample S with n elements from performance testing in step 1. And to simplify this demonstration, we set n to 9. We then will use the basic bootstrapping to construct the very first bootstrapping resamples. To start with, we first randomly join elements from sample S with replacement, and then we randomly join another elements with replacement from sample S. We repeat the drawing again and again for in total 9 times. After that, we have successfully constructed S1 star. We then repeat the whole drawing process again and again and again for in total of C times. Then we have successfully constructed C groups of basic bootstrapping resamples. After that, from each resample set, we can easily obtain the mean performance from mu1 to mu-c, and based on the mu's, we can easily generate the distribution for mean performance. From the distribution, we can easily establish the confidence interval for the mean performance, and the confidence interval is typically viewed as margin of error. After that, basic BT will use the width of the confidence interval to determine the stop criteria and the accuracy of the testing results. To demonstrate that basic bootstrapping cannot keep the internal data dependency, we calculate the autocorrelation of basic BT as well as the original data. We can see from the table that the autocorrelation of basic BT is different from the autocorrelation of the original data, and 0 ACF scores means basic BT failed to keep any internal data dependency. To solve the issue, we find another advanced form of bootstrapping named block bootstrapping. By calculating the autocorrelation score of block bootstrapping, we can see that it has the same level of autocorrelation scores as the original data, which means block bootstrapping can keep the internal dependency within cloud performance data. On the graph, it also shows the same information that block bootstrapping can keep the internal dependency within cloud performance data, while the basic bootstrapping cannot. On the left-hand side is an example of block bootstrapping. We first have initial sample S with 9 elements. To simplify the demonstration, we set the block size to 3. The very first step of block bootstrapping is to connect any adjacent 3 elements into a block, which means the first block will be 0, 1, 2, and the second block will be 1, 2, 3, and the third block will be 2, 3, 4, and so on and so forth until all the blocks are constructed. Then we will use block bootstrapping to generate C groups of bootstrap resamples. First, we construct S1 star, the very first resample set. We first randomly draw an block with replacement from sample S, and then we draw another block with replacement. We stop until all 3 blocks are selected and that's 9 elements are selected. We have successfully constructed S1 star. We repeat the whole drawing process again and again for in total of C times. We have successfully constructed C groups of block bootstrapping resamples. In previous example, we set the block size to 3. However, according to our study, using block bootstrapping with fixed block size to replace the basic bootstrapping cannot always improve the accuracy of the testing results. On the graph is 100 performance tests using basic BT methodology that produce results with less than 3% errors. We can see from the graph that while replacing basic bootstrapping with block bootstrapping using fixed block size, for most of the applications, the accuracy have been improved. However, for this example, the accuracy even decreased, and this reflects the issue that proper block size depends on the behavior of the cloud application and the cloud platforms. To solve the issue, we adopted automatic block length selection for the dependent bootstrap to estimate the optimal block size. By replacing basic bootstrapping with block bootstrapping and the optimal block size, we can see from the graph that for those specifically for application, the accuracy increased to 100% for all of them. Based on the observation, we designed Mateer, which is a measurement-based performance testing methodology. Mateer determines the stop criteria using non-parametric block bootstrapping with automatic block length selection. Mateer can provide reliable stop criteria for users to obtain highly accurate results in the form of single point of estimates. Single point of estimates can be mean performance, median performance, 90th performance, or any other percentile of performance based on the user's interests. The goals for Mateer is to provide highly accurate results at low testing cost. In the next few slides, I'm gonna use one example to demonstrate how Mateer works. In step 1, we first run the application for 1 day to obtain the sample set S. And in step 2, we will run the application for another day to obtain the sample set as new. In step 3, we combine the data from step 1 and step 2 into a new set S prime. The output from this step including the sample set S and S prime. In step 4, Material will determine the accuracy using block bootstrapping. First, we have the initial sample S with an element from previous step. By applying block bootstrapping, we can generate C groups of block bootstrapping resamples. And for each resample, we can easily calculate the single point of estimates. In this example, we use mean performance as the target single point of estimates. So we can easily obtain the mean performance from mu1 to mu-c. After we successfully obtained mu1 to mu-c, we do the same to the sample set S prime to obtain the mean performance from mu1 prime to mu-c prime. And accordingly, we can easily calculate the percentage error delta from delta 1 to delta c. After that, we will take one specific delta based on the user predefined confidence level, and we call it delta confidence level. Finally, we will compare the delta confidence level to the user predefined maximum allowed error. If it's within the error, we can stop our testing and report the results. If it's not, we have to continue testing. The intuition here is that taking bootstrapping results at high confidence level enlarges the possible delta between the original samples. If delta confidence level is within the maximum allowed error, then the results from original sample are likely to be accurate. If delta confidence level is larger than the user predefined threshold, we have to go back to step 2 for additional test runs, and then combine the newly obtained data and continue the rest steps of material until accurate testing results are found. We use all 33 benchmark VM configurations from PT4Cloud to evaluate material. We evaluate material to answer the following two questions. First, how accurate is material and what's the cost benefit of material? On the two tables are the benchmark domains and the VM configurations of PT4Cloud dataset. First, we evaluate the accuracy of material. We define the accuracy as the percentage of the tests that provided performance results with less than maximum allowed errors. In this evaluation, we use 90-tile performance as the target single point of estimates and 3% as the maximum allowed error. We can see from the graph that material is very accurate. It has an average accuracy of more than 98%. The worst one of material probably is the YCSB benchmark on Chameleon Large. Only 50% of the test runs can provide the results with less than 3% errors. However, even for this application, the maximum error is only around 4%, which means material is still very accurate. In our paper, we also evaluate using mean performance. In addition to use 3% as the maximum allowed error, we also use 5% and 10% as the maximum allowed error. We can see from the graph there are also 90-tile performance as the target single point of estimates. We can see that for most of the applications, material have better accuracy than basic BT and COV. While comparing material to PT4Cloud, for most of the cases, they have same level of accuracy. However, when the maximum allowed error is low, and especially on Chameleon Cloud, material still have better accuracy than PT4Cloud. Next, we are gonna evaluate the cost benefit of material using number of test runs. We can see from the graph that while providing the same level of accuracy, material only requires less than 1/3 of the data as PT4Cloud. And we can also see that material needs more data than COV, and basic BT. This is because those two methodologies cannot accurately determine the stop criteria, which leads to the early termination, and that causes the inaccurate testing results. In conclusion, we find that internal dependency exists within cloud performance test data, and it must be taken into consideration to obtain accurate cloud performance results. And based on our observations, we designed Meteor, a reliable automated cloud performance testing methodology based on block bootstrapping, law of large numbers, and autocorrelation. We also perform a thorough evaluation to evaluate the accuracy of Meteor and state-of-the-art testing methodologies. Experimental evaluation on two public clouds showed that while adopting 3% as the maximum allowed error, 98% of Meteor's tests are accurate.